Hi, in this video I'm going to go through the week 1 poll for spring of 2024. In this poll I go through questions related to sequencing technology, specifically how it interacts with the different technologies that have come through the years and how that may affect the types of data that we see in current times. So one of the major advances through the years has been the ability to deal with repetitive sequence. And so if you had simply ranked these in order of the kind of like age of the technology, it would actually be the right answer. So the worst for repetitive sequence would end up being the 150 base pair. The moderate for repetitive sequence would be the paired end, and the best would be the 1,000. But that's not really the way I wanted you to kind of go about answering this question. What I was really hoping for you to come up with is this concept of what repetitive sequence is. And there's kind of two-ish major categories that most people are referring to when they say repetitive sequence. One is going to be kind of the classic repeat, so like ATG, 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 ATG. That would be a trinucleotide simple tandem repeat or simple sequence repeat or even microsatellite if you're talking to specific people. These repeats are extremely common. They're all throughout the genome, and so one looks exactly like the other. The context is different. It's on a different section of the genome, but it's exactly the same. And so if I have a 150 base pair sequence and it lands in the middle of that repeat, well, that could come from any number of 150 plus base pair repeats of the sequence ATG, ATG. That's the issue. That's the issue with repetitive sequence. I think a little bit, maybe even easier for students to understand is transposons. So transposons are sequences that copy themselves, or they're somehow, they trigger the copying of themselves into different places throughout the genome, kind of like a virus. In fact, many of them have virus-based origins. Well, these transposons, even though they're internally not repetitive, or at least that's not the general idea, on the whole, so throughout the genome, they're incredibly repetitive. It's the same sequence copied all the way throughout the genome. And so even though it's kind of got a unique sequence in terms of like its structure, it's not repetitive, it's not a palindrome and stuff like that, despite it having these interesting sequences, it's a sequence present all over the place. I don't know if I'm seeing the chromosome 1 left side version or if I'm seeing the chromosome 7 version. And so for sequences like this, so these repetitive sequences, an umbrella term used to refer to them, the ability to land a sequencing fragment, to source a sequencing fragment from a unique region of the genome, something that I know where it fits in, that's the goal. That way we know where it belongs. And so a 150 base pair read, just being a small single sample of the genome, is not going to be your best option. The 75 base paired end reads, so 75 on each end, adding up to 150 just so it was a little bit more comparable for you guys. But the fact that it's separated by a larger size, what we call the insert size, because it's separated by a larger size means one of those sides is more likely to land within a unique region. And that's the goal. That's how we figure out that it's where it belongs. And then finally, the 1,000 base pair reads, definitely the best case scenario, bypasses all of these issues because it simply sequences all the way through. And usually the trade-off there is going to be the depth, and really right now it's more the cost. Although that's rapidly decreasing as the technology is getting cheaper and cheaper. The next question was the major advancement between the first and next generation or second generation sequencing systems. I was trying to get you to look at the DNA solution itself, with the answer being that it's the major difference, and there's a lot of differences, but the biggest by far difference is the number of different sequences that can be within that DNA solution. So I can have like a tube of DNA, but for Sanger sequencing, that DNA needs to pretty much all be the same sequence. And that way, whenever it starts to light up, because of the Sanger sequencing method, it all lights up in the same color, and that's how we determine its sequence. However, because next generation sequencing occurs at a much smaller level, we can have individual different fragments of DNA, and they can all get sequenced at the same time. And that's why it was such a tremendous increase in the rate of our ability to get genetic information, because we went from one sequence per one tube to millions of sequences per one tube. I mean, it's just an enormous difference. And that was the big jump. And in fact, we still use Sanger sequencing. It is excellent if you have a single sequence that you need to know. It's still kind of my go-to method. But next generation sequencing, anytime I need to know something any more abstract than a single PCR product at a time, I go for next generation or some other related system that does parallel sequencing. Okay, so this next one was trying to get you to just think through this this formula I gave you, that the formula for genetic coverage, so essentially given a certain amount of DNA in an organism's genome, how often per locus do I expect to observe that genome on average? So the example I gave was that for me and that device, that if I take the number of reads and base pairs that it totally generates, and I divide that by my total genome size, this is about 30. I had about 30x coverage from a single one of those very nice sequencing devices. Well, here, if I'm trying to calculate how many total base pairs are sequenced, I can use some of these numbers. So I have 2 million paired end reads. That's the number of reads. It's not the number of base pairs. So that doesn't give me my answer by itself, but it is related. The more reads you have, the more sequence gets covered. But I need base pairs, so I have to keep going. So here I have a read having 50 base pairs per end sequence. So that means per end of the fragment, I'll have 50 base pairs. So a lot of students are going to tell me 50. So they're going to try to take 2 million, multiply it by 50, but it's per end. So it'd be 100, right? 100 base pairs, 50 on each end. So each read equating 100 total base pairs. So 2 million times 100 base pairs per read gives us the total number of base pairs, or 200 million base pairs. I'm then going to divide it by the total amount of space, so like the genomic space that this is going to be divided up between, and that's going to be the size of our genome. If I want to know, like on a per locus basis, I would want to divide it by the haploid genome size, so like the length of a single copy of the genome. If I do care about things like heterozygosity, I might want to divide it by the ploidy number times the haploid genome size, but that's getting a little bit more advanced. But just go back to your basic grade school math. It's the amount of total divided by how many different portions that you are dividing it between. And that's the calculation. It's just using big words and big numbers. So anyways, it's going to be 200 million, the reads times the length per read, giving us the base pairs total, divided by the size of the genome, again in base pairs so that they're all comparable. And so you need to just figure out giga. Well, million is mega. Kind of put these next to each other just to help clue you in. So this would be mega base. This is giga base. And this would be, I guess, tera. Yeah, tera base. Nobody, well, these days, I'm sure people are at times talking about tera base, but there we go. There's gigabase right here. So this will be x times y. So you could either do this one times this one or this one times this one. Because of this line of text, this was the right answer. for the exam, I'm going to have to figure out a different way to answer this. Maybe I just give y'all calculator access. Excuse me. Ooh, I need to sneeze. So the rest of this doesn't have a correct answer. The only other thing I wanted to mention was some of these questions on who you should contact. I was quite happy. Everybody seems to have understood things. If a student is struggling with a single homework question and they're just looking for help with the question, Slack channel. Like, that's the whole point. It's meant to be fast. It's collaborative. You can comment on other people's things. As long as you're not just actively giving away answers to questions, we're happy. We want y'all discussing and interacting with these concepts and learning. That's our major goal. So Slack channel, absolutely. Anything to do with grades and grading will need to go through these more official channels, so Canvas or GradeScope. In this case, if since you submit homework to GradeScope, it actually has a built-in system for being like, I want you to take a look at this one again. It's a great system, so you would just do GradeScope. And I put it's this one because y'all don't know this. Y'all haven't gone through the process yet, but that's what it'll be. You'll go through GradeScope. Finally, a student just having issues with the class structure, wanting tips on how to study, or really just a lot of different situations, come to me. So just come to me. I prefer Slack. There's a lot of ways you could actually get in contact with me, but Slack is going to be your best option because I check it constantly. Because again, it's meant to be this kind of rapid back and forth. If you want something formal, you want to talk about like accommodations, and you want a record of the conversation, I totally get that. You can go through Canvas or email, and those should get you there. As long as it's not about grades. I can't talk about grades through email. Like grades directly. I received a late penalty for a homework. Really, the answer is just that Sanishka is in charge of late penalties, and that's just to help ease my burden with the class. So anything having to do with the late work penalty, start with her. She can work with me if there's any issues. It's just a big system, so it helps to have that. So anyways, thank you so much. Hopefully that helped. Please reach out if you have any other questions. Again, the Slack, not like YouTube comments, is going to be your best choice. So thank you.